Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we are happy to have Tauhid Zaman here from next door, from LIDS, the Laboratory of Information and Decision Systems at MIT. And he is going to be talking about knowledge in networks, rumors, superstars, and communities. And I think that's probably the sexiest title we've had for any of these talks. So you win the sexy title award, definitely. I'm just trying to waste time as these people walk in. Okay, good.
All right, thanks, Jennifer. And I guess I'll just jump into it here. So networks and knowledge. So networks are becoming a bigger part of our lives these days, especially social networks. So this here is a picture of a portion of the Twitter network. And another very huge popular network is Facebook. And these networks, they're very large and they're very complex. So what I want to ask in this talk is there knowledge in that complex, messy structure? And if there is knowledge in there, how do I get that knowledge out of the network? And I'm going to ask this question 3 specific problems. So the first problem I'm going to look at is the problem of finding a rumor source in a network. So imagine there's like a cyber attack in the internet, some kind of worm spreads around, and I want to find the source of the cyber attack. Or maybe some kind of virus spreads in a human population, and I want to find patient 0. Or maybe just more abstractly, some kind of rumor or trend or something is spreading in a network, and I want to find the source of this rumor. So the question I want to ask here is, if I just knew the guys that are infected with the rumor, so just that rumor graph, can I use that structure to figure out who the source was? Okay, second question is predicting superstars. So for those who don't know, this is Justin Bieber. He's a teen pop sensation. And he's interesting because the way he began was he put a video on YouTube, and people started to like it. And they spread it around, spread it around, spread it around. And then one day you wake up, and a superstar is born, right? And you're like, how did that happen? So what I want to ask is, could I have predicted his emergence? Could I have watched that network growing and then said, no, he's going to be a superstar. He's going to reach this many people in this amount of time. Now, that's kind of an ambitious goal. So maybe the first step to answer that question is there a growth mechanism for these kind of networks? Like, is there a way to predict how they actually grow? Okay. And finally, communities. So this is a Facebook network. And if I gave you someone's Facebook network, a natural question to ask is, what are the communities in the network? So here I've labeled a couple of communities with social labels. But what if I give this to a computer, Can the computer learn the number of communities and who's in the communities just from the structure of that network alone and nothing else? Right? So a community is kind of the person that has to look at their network. Okay, it's hard to cluster exactly, so you try to do the best you can. Like you say, these are my high school friends, these are my work friends, etc.
You're asking whether the computer can do this.
Right. Can the computer look at the structure, not the social
information?
information?
Have to be disjoint.
They don't have to be, right?
Okay.
So now it's the overview of the talk. I'm going to answer these 3 questions, these 3 network problems, the rumor sources, superstars, and communities. And the unifying theme of these 3 problems is this notion of network centrality. So what's this? So if I give you a network like this, a question I can ask you is, what is the center of the network, right? The problem is that's kind of an ill-defined question because how do you mean center, right? For example, this guy is the degree center because he has the highest degree in the network. This guy is the distance center. He's the closest to all the other guys in the network. But in general, there's many kinds of network centralities. And the question is, for the problem you want to solve, what is the right one to use? And then more importantly, how do you use that centrality measure to get the knowledge out of the network, right? So this will be the theme of this talk. So let's start with the first problem of finding rumor sources in networks. So I'm going to begin with a very simple model for how a rumor spreads. So in my model, I'll assume there's a uniform probability of anybody being the source a priori. So I have no knowledge of who is the source beforehand. And second, in my model, once I have the rumor, the time to infect my neighbor is going to be random, but it's going to be an exponential random variable.
So this is like an epidemic model as
Exactly.
opposed to a game theoretic model. Like there was recently a paper by Montanari and Montanari and Severi in PNAS, which was contrasting the epidemic model with other models of how innovation or things like.
So this model, as you said, is an epidemic. It's like an extension of the susceptible infected model used in the epidemic literature, right? And I'm basically going to assume this model throughout this part of the talk. And also on this model, all the edges have the same rate lambda for infection. So everybody kind of infects their neighbors with the same rates. So with this model, I'm going to construct a rumor source estimator. So I'm going to assume I know the rumor graph G. So if I come to the network, all I know is these nodes have the rumor in red. I know the edges between them, but I have no knowledge of when they heard the rumor. I have no temporal knowledge at all. So now on the surface, this is kind of a hard problem, right? It's like finding a needle in a network haystack. Let's try to formalize this, right? So what I want is a node V star, right, that maximizes the probability that the source is node V given the rumor graph G, given my data, right? So let me apply Bayes' law to this expression. I get the product of the likelihood of the rumor graph given the source was node V times the prior probability of V being the source. But now recall my model, I'm assuming that the prior is uniform. So let's forget about that prior. And let's focus on this likelihood. How do I calculate this expression? So a key idea to calculate the likelihood is this idea of spreading orders. So I don't know the actual rumor spreading order. If I knew that, then I'm done. The first guy is the source. But I have our constraints on how the rumors spread. For example, if these 4 nodes are my rumor graph, let's say the source was node 1, right? So how could 1 create this graph? One spreading order is 1 tells 2, 1 tells 3, and then 3 tells 4. Another one is 1 tells 3, then 3 tells 4, or then 1 tells 2, sorry, then 3 tells 4. And the final order is 1 tells 3, 3 tells 4, and then 1 tells 2. So these 3 orders are the only way 1 can create this graph. Contrast that with 2 being the source. Had 2 been the source, there's only 1 spreading order. 2, 1, 3, 4, right? Now, the question you would ask here is, what is the probability of every ordering? Because if I knew the probability, I could just add these up to get the likelihood. So let's see if I can calculate these probabilities in a nice way. So it turns out that on a regular tree, the problem becomes very simple. This is where I began my analysis. So a regular tree, every node has the same degree, and there's no cycles in the graph. And now the memoryless property of my spreading times, because they're exponentials, they're memoryless, combined with the fact I have a uniform rate of spreading for all the edges in the graph.
Can I ask a clarifying question?
Sure.
So your model, you had this exponential spreading rate.
Right.
And do you have the standard, how do you die out? Because otherwise everybody...
So in this model, I assume it's like a rumor spreading model, so nothing really dies out. So in the model,
eventually, if you waited long enough, everybody would be infected.
Right. So the thing I didn't mention is that I'm assuming throughout this part of the talk, it's a bit more theoretical, that the underlying graph is infinite, that it just basically keeps going. Now I'm going to talk about real networks at the second part of this section, so we'll get back to that. But right now, assume the underlying graph was...
I see that the regular tree gets rid of this, but I would have thought in the general problem you were going to need also a prior.
Right. So we'll get to that question also, right? This is the beginning of this analysis, right? We'll get to the more complex real situations in a second. So on the regular tree, right, these 3 properties give me the fact that all the spreading orders are equally likely. So let's see why that's the case. So imagine this is my rumor graph, the 4 nodes, and I want to calculate the likelihood of G given the source is 2. So there's 2 spreading orders that give me this graph, 2, 1, 3, 4, 2, 1, 4, 3, right? These 2 events. So let's look at the probability of this first event, probability 2, 1, 3, 4. So 2 is my source in the black here. The rumor boundary, the place where I can spread the rumor next, are these 3 nodes. They're all the same random variable, so the chance of picking 1 next is going to be 1/3. So 1/3 I affect 1 next. Then the rumor boundary grows to 4 nodes, right? So now, because it's memoryless, these 2 edges reset essentially. So the chance of picking 3 next is going to be 1/4. 3 is infected, the boundary goes to 5 nodes, things reset, I pick 4 with probability 1/5. Now that's the same probability for also the other ordering. And in fact, any ordering in this graph with that 4 nodes will have the same probability. So my likelihood is equal to 2, which is the number of orderings, times this ordering probability, right? So now I kind of simplify the problem a bit, because now it's a counting problem. Because if I count the number of orderings in this regular tree, I essentially have my likelihood. So let's try to count these orderings. So to do that, I need a couple of definitions. So first, I'll define R of V comma G as the number of orders of G when I fix that source V. So you can think of R of this R, V, comma, G, it's sort of like the number of linear extensions. If you think of the graph as like a partially ordered set, if you fix a source node, or also like the number of topological sortings of this directed graph. So in this notation, my likelihood is proportional to this R, V, comma, G. So that's the object interest. And next I define these subtree variables, T, V, K. So this is the number of nodes and subtree with K as a root, V as a source. So let me explain that. If my V is 1, that's my source node I assume for this rumor. My K is 4, let's say. It's the root of the subtree I care about. Then T14 is going to be 3 because there's 3 nodes in that subtree. All right, so with this definition, let's try to calculate the number of orderings. Let's do an example on this graph here.
Why does the root matter?
The root matters because I'm assuming that I want to calculate your likelihood. So I pretend you were the source. And then I say how many ways you could have created that rumor. Because the more ways you can create it, the more likely you are to have been the source.
So he's cutting off the edge from on the last edge on the path from the root to the source, or from the source to the root, right? That's
Right. You have to fix this root because you want to basically make the tree point away from the source, right? I'll need this definition.
Treating 1 as the source of the
I
rumor.
understand the 1 as the source. I don't understand 4 as the root.
Well, so I'll need this definition because in the next slide you'll see why this isn't. Why I have to kind of define this.
Use RVG in terms of TVK.
Exactly. So let's do an example, see why these actually pop up in this expression. So this is the network I'm going to look at for an example. And we'll say the source is 1. Let's find the number of ways to order these nodes, given that 1 is the source. So R of 1, comma G. So in any spreading order, there's going to be 8 nodes in this network. The first node has to be node 1. That's my fixed source. So I have 7 nodes left. From the 7, I choose 1 for a subtree T12, this subtree. I can order those nodes R of 2, T12 ways. But that's just one way to order the nodes within the subtree. It's just one node. Okay? I have 6 left. I'll choose 3 nodes for this subtree here, T13. I can order these nodes R of 3, T13 ways. But this is 2. It's 3, 5, 8, 3, 8, 5. Okay? So now I have 3 slots left. I'll choose 3 of those slots for the final subtree, T14. I'll order those R of 4, T14 ways, which is just 2 ways. Now if I take this expression, I just simplify it, it looks like this. And I wrote it this way on purpose to kind of show you the structure. So in the numerator is 8 factorial. 8's the size of my network. It's like n, let's say. I have 8 in the denominator. So think of 8 here as being T11. It's node 1's subtree when 1 is the source. The 1, the 3, and the 3 are these 3 subtrees here. And the 4 ones are these subtrees of 7, 6, 8, and 5. So I get in the denominator every subtree multiplied together when I fix that source. And in fact, this is the general formula for the number of orderings when you fix a node on a tree G. For any tree, not just a regular tree. It's this formula here. N factorial divided by the product of all the subtrees when you fix your source. So this function, I called it rumor centrality. It's like a new kind of network centrality measure for this rumor source problem. And what's nice about rumor centrality is that rumor centrality is the exact ML estimator for the regular tree. So it is the correct centrality measure for that specific graph under that spreading model. So a question I want to ask now, a bit more theoretical, is how good is ML estimation? Can I calculate detection probabilities, etc.? So let's look at this question next. So the key idea that I'll need to kind of establish these ML detection, question? ML is maximum likelihood. Maximum likelihood.
Oh, okay.
So it's like the best estimator you can do to minimize estimation error.
Okay. So this only works if the graph is a regular tree.
So it's ML when it's a regular tree only.
And it has to be infinite, right? Like everything.
Right, you have to assume no boundary effects. Right. So it's a more theoretical approach.
So what's a regular tree?
A regular tree is a tree where every node has the exact same degree, and there's no cycles in the network. Okay. So I'll need some intuition for this rumor centrality, like what it's telling me. So here's a tree here. And pretend that for a second this node V star was my rumor center, which means it has the maximal value of this rumor centrality of the network. Now let's look at rumor centrality of V star and his neighbor J, one of his neighbors. So by definition, R of V star G is going to be bigger than R of JG, because he's the rumor center. Which means that the product of his subtrees is smaller than the product of J's subtrees, again by definition. But now note that the subtrees in these products are the same for the most part. In fact, they're all the same, because if V star is the source or he's the source, all the subtrees in here have the same number of nodes. Right? except for two trees, right? When V star is the source, he has this tree here, T V star J. When J is my source, I have this tree TJ V star. So they're the only guys that survive in that formula. But now, what is TJ V star, the one over here? Well, it's all the nodes in the network, N, minus the nodes in the other subtree, TV star J. Right? Now I just take this one more step, and I get that TV star J is less than N by 2. So any neighbor of the rumor center can't have more than half the nodes in his subtree. Or in other words, the network is balanced around the rumor center. So now you kind of see where I want to get correct detection, right? So if I have a scenario where the rumors spread from the source in a network in a kind of a balanced manner, balanced in this sense, when I apply rumor centrality to my network, I want to get correct detection, right? I'll find the rumor center equals the rumor source. So let's see now where this happens or how this happens. So first I looked at a really simple topology, a linear graph, just a line like this. And I'm going to define CT as the event that I correctly detect the source after it spreads for a time t with rumor centrality.
Just go back. So
To here.
if you have d neighbors, you might expect that you have like this tree of tj v star is like n over d or something like that.
Well, so remember the rumor spreads in a random manner, right? So it could be that when it spreads from the source, it spreads maybe randomly in one direction more than the other guys. So we'll see where that effect kind of pops up in about 3 slides. So if we can get back to that question. So first, linear graphs, right? So CT is my correct detection event. So I established the following result. So for regular tree, with d equals 2, if the rumor spreads for a time t, then the detection probability scales as 1 over root t, which goes to 0 as t goes to infinity. So what this means is that in a linear graph, this really simple topology, if I'm a rumor source, I can hide really easily. And I can hide because there's not enough structure in this network to actually extract, there's no knowledge to extract from there. So how do I get this result? Just like a quick intuition for it. So when I spread a rumor from a source here, it's like 2 Poisson processes going opposite directions because all these edges are exponential random variables. Okay. I'm going to get correct detection when it's like perfectly balanced Poisson process. So after t seconds, there's exactly the same number of infections on both sides. Now in a Poisson process, like the variations are like order root t, and that's how you get that result. Okay, question? So the centrality is actually, it's kind of like smooth and spread out. So the maximum likelihood is a center, but then it kind of, it's like it doesn't concentrate enough, right? The center guy isn't that central, which is why like.
Is it Gaussian or how does it look?
Oh, it's probably
It's
broader.
probably, how does it look exactly? It's like a combinatorial formula for the centrality. It's not exactly Gaussian, so I can't say that. It has like a weird shape to it. But it's like a kind of curvy shape like that. But I didn't really look at the structure of that actual distribution.
And on the infinite line, it actually is just.
And so it converges to like a flat thing in the
Yeah,
world.
yeah. it would
Whereas
have to
this one
converge
holds
to
on the
uniform.
infinite line, right? So if you
But basically, you have like the graph looks like an interval, and then this middle square root t nodes in the interval are each basically have the same.
Roughly the
chance of being
same,
the
yeah.
source.
So that's why you get this routine.
It's gonna, I would expect it to be much more spread out than a Gaussian. Have bigger
But-
tails,
The important part is,
boring.
but. What?
Linear graphs are boring.
yeah,
Yes.
let's get some good stuff, right? Good question. All right, so what's next? This is kind of boring, like you said. So now I look at a geometric tree. So these trees are parameterized by a parameter alpha, which kind of describes their growth. So what it is that the number of nodes at distance L in these geometric trees scales as L to the power alpha. So they have polynomial growth. So for these kind of trees, I got the following result. For a geometric tree, where alpha is strictly greater than 0, because alpha equals 0, this is essentially a linear graph again. So strictly greater than 0. If the rumor spreads for time t from a source with degree greater than 2, one more caveat, then in this scenario, the detection probability converges to 1. So I always get correct detection on these geometric trees asymptotically, right? This means that this kind of estimate, while it's not ML on a geometric tree in general, it's still as good as any ML estimator you could possibly think of because it's one detection. So how do I get this result? So in a brief proof outline. So the key idea to prove this theorem was this thing called a shape theorem. So a shape theorem is the idea from the field of first passage percolation theory. And the idea of a shape theorem is that after a long time, I can roughly characterize the shape of the rumor graph. So let's see what the shape I established for these kind of graphs. So it's like in this cartoon here. So let me explain this cartoon to you. So define epsilon to be t to the minus 1/2 plus delta for some small delta. So this epsilon is going to 0 as t is getting bigger. Then I showed that the tree is full within 1 minus epsilon t hops of the source. So if this is my source here, then within this many hops, everybody has the rumor. Everybody's heard what's going on. Then I showed that beyond 1 plus epsilon times t hops, nobody has the rumor. So beyond here, nobody has heard anything. And then there's an epsilon fraction node in this boundary region where some guys have the rumor and some guys don't. But it's only an epsilon fraction of the bulk here, right? So take that shape of the rumor graph. And then for large T, because I have at least 3 neighbors in my source, none of those guys can have more than half the total nodes in the network. And hence, asymptotically, I always get correct detection. So it's spreading in a balanced manner on this kind of geometric tree.
I mean, essentially, you're still working on infinite trees.
Still infinite, so theoretical
So
infinite
what
stuff.
does it mean, half the total nodes?
Because it has at least
For a fixed T,
it
right?
spreads out from somebody who has at least 3 neighbors. That's why.
But I don't understand. What is half the nodes of an infinite
So basically, you
tree?
fix a T, and then you apply the centrality estimator, you'll get some detection probability. And then you take that probability, and you keep making T bigger and bigger and bigger, it's going to go to 1. So
it's not just more than half. It's just 1 over d, like what, more or less.
They're roughly the same size, actually, depending on the regularity of the graph. So there's one more regularity condition in the graph that none of those subtrees have. They kind of have the same number of nodes in them and the underlying structure. Then everybody gets filled up, and you get balance.
So up to epsilon, all the
Exactly.
Yeah, the same.
So, I understand that the sort of mathematical model that led to this,
Yep.
but what scenario or what rumor has this sort of spreading, like, what spreads like this in real life? Or
So this model I proposed to you is actually used in like the epidemic literature to kind of model how viruses spread in human populations. So it's been used for a long time by epidemiologists to kind of model called the contact process. So how viruses spread, and it's just a model to use, and it's been accepted through literature to model human interactions.
So is an assumption that that the rumor is constant, that there's no change, there's no mutation of what the rumor is? 'Cause it sounds
Right,
like
it's the
you're
same
assuming
thing.
It's the same message moving out. There's
Exactly.
no modification as it's heard by, as it's passed along.
So it's one abstract object that's kind of spreading that people are passing around.
We're going to get more realistic story later.
We'll get to that in a few more slides. I promise.
We should stop bitching about the fact that this isn't realistic.
Right, we'll get the real stuff.
Sorry, can you explain again what a geometric tree is?
So the geometric tree is basically, if I'm a node in the tree and I go out L hops from me, and like how many nodes are L hops away from me, that number grows as L to the power alpha. So it's like a polynomial number of nodes, L hops from me. So the graph isn't growing too fast.
Okay.
Right?
So I'm confused though, because your previous combinatorial formula, that doesn't work for this.
So that formula works. That gives you the number of orderings on any tree. Right?
Okay, yes.
It's ML on the regular tree.
Okay, yeah.
It's not ML here, but as the result shows, it works as good as ML here.
Okay, I see, okay.
So now let's go to the case where it was ML. Right? Regular trees, where this was an ML estimator. Let's see what happens. So regular trees, number of nodes at distance L grows as d to the minus 1 to the power L. Or d is equal. So it's exponential growth. It's an expansion tree. Let's see what happens here. So for these trees, I showed that for a regular tree with degree d greater than 2, if the rumor spreads for a time t, then the detection probability is lower bounded by a strictly positive constant. So compare this with the linear graph where that went to 0 exactly and the limit is t. Here it's saying it hits a floor. So no matter how big the graph gets, I can always get non-trivial detection of the source. They get even nicer result if I look at a regular 3 tree. So here I showed for a regular tree with degree d equals 3, if the rumor spreads for time t, then this detection probability goes to 1/4 exactly. So you get a nice clean result for a regular 3 tree.
Can you also say that you get a list of, say, 4 candidates that with probability 10 into 1, the rumor center is one of them?
So I haven't proven exactly that it kind of concentrates around a few hops of the source, but I've seen empirically it does actually in simulations that the error is within 1 or 2 hops of the source for like hundreds of nodes rumor graphs. So it seems to be a concentration effect happening. So let's see how I get this kind of proofs, right? So naturally I just want to use shape theorems again, right? But the problem is with these kind of expanding graphs, you can't use a shape theorem because the size of the boundary of these graphs is roughly the size of the interior. So there's too much variation to control. So instead I have to really use a balance property of rumor centrality to get these results. So what I do is I have to work with the subtree size distribution explicitly. So these random processes here, these t variables is the number of nodes in the subtree as a function of time. I got to find these distributions of these things exactly. And then I get the lower bounds by combining that subtree distribution plus the balanced argument for rumor centrality, and then plus some non-trivial analysis I'm not going to go into here because it's really just not worth the effort, but it's there to get these lower bounds. Okay, so that's the theory part of this section. So now let's get to some real stuff, right? So a general network. So in a general network, you can actually draw some of the ideas from the trees with you. For example, this idea of a spreading tree. So even though the graph may have cycles in real life, the actual spreading process is a tree, because once I have the rumor from somebody, I can't really get it again. So there has to be a tree corresponding to how it's spread. The problem is there's too many trees in a real graph to keep track of. So I propose this following heuristic. Let's just keep the breadth first search tree of a node. And here's what I mean by that. So imagine this is my rumor graph, these nodes. Let's say A was the source I'm looking at, right? And I want to find his likelihood. I pretend that his spreading happened on his breadth first search tree. So these red edges are his breadth first search tree. So I assume it happened on that tree, and then I use that to do my analysis. And the second thing I have to look at is his spreading, so this corresponds to the fast rumor spreading, because I tell my friends, they tell their friends in that order. So that's the heuristic idea behind that. Next is spreading orders. So unlike regular trees, in a general graph, not all spreading orders have the same probability. And the problem is I can't keep track of all the spreading orders. There's just way too many of them. So again, I use the same kind of heuristic. I'm going to assume that every spreading order is equivalent to the breadth first search spreading order. By that I mean, I would assume for node A that every spreading order he has a probability of this spreading order, the order in which I constructed his breadth first search tree. A, B, C, D, E, right? And the idea is that this is kind of like the typical probability he's going to see for all of his spreading orders. With these heuristics, I approximate the likelihood of the node, A, as the rumor centrality on his corresponding breadth first search tree times the probability of his typical BFS spreading order. So it's like its number of spreading orders, approximation, times the probability of the spreading orders, approximation, right? Now for this estimator, I couldn't get any theoretical results thus far. So instead I tried to try it out empirically and see if it works on like some real topologies. So the first network I looked at was the Internet Autonomous System Network. This is a real topology. And here a rumor spreading is like a computer virus spreading. So I did my experiment. I took the network. I would simulate the rumor spreading according to my model to 400 nodes, make a bunch of rumor graphs, apply rumor centrality to the network, and then apply rumor centrality with this BFS spreading order correction to it. And I just collect the error of the estimator from the true source and just plot that in the histogram. So here's the rumor centrality estimator error. And here's the estimator error with the BFS spreading order. And you see this BFS spreading order actually kind of shifts the error to lower values. And in fact, I even get correct detection when I never got it with the rumor centrality. So it seems this heuristic is kind of working well to improve performance. Next, I look at the US power grid network.
So what's the rumor centrality measure itself?
So it's just you make the BFS tree, and you find this rumor centrality. You do it for every node. You pick the maximum guy, and then that's your estimate of the source. And this is with that probability of the spreading order attached. This graph is just rumor centrality without that BFS correction, right? So remember, this is the BFS correction here. So once it's just rumor centrality, one's both these things. What it's kind of showing is that this degree of heterogeneity in the network really can ruin things. So this kind of corrects for that a little bit.
No, you still have, so the point is, you take the real network, but then you
simulate spreading on it.
Simulate spreading with your model of spreads.
Exactly. If I could have found data on real spreading, with where you do the source, and you could try this, I would have loved to try that, but I couldn't get my hands on that kind of data at that point. So next I tried the US power grid.
Just to get a flavor of how well this estimator is doing. So you
Sure.
show that the error is around 2 or 3 hops
So
away, whatever.
in these networks, right, the rumor graphs, their diameter was like 10 hops.
Okay.
So the diameter is 10 hops. I'm getting, with this correction, within 20%, I have within 1 hop of the source.
Okay. How many points are within
Great.
2 or 3 hops?
So that depends on who your source was. So I pick a random source every time, and then I spread it, right? The problem is in this network, there's some hubs, and there's some like low degree nodes. So let's say how many nodes were, this many hops away, depends on who I picked. But I picked them at random, so I can't really quantify how many hops there were. There could have been many if I picked this guy. It could have been a few if I picked
Well,
this guy.
But you could say in your simulations how many points, of the, I presume you did some number of random
Right.
trials, and in those random trials, what was the average number of things were within 2 of the...
So actually, I didn't look at that number for
Okay.
when I did the trials. I just looked at the error of the guy from the true guy.
But it makes sense. I mean, you don't know now if these probabilities. It's a very big difference when you picked for the root like the tier, right? If you picked
Right.
a hub or you picked a leaf node, and
So with regards to that,
you should really separate the graphs to.
I agree. But the problem was that under the simulation, at that point I didn't consider that the leaves and the hubs would be such different. They imply different things for the error performance.
Have you had a chance to compare it to the case that you picked the rumor center as the degree center or the infinity center?
So I didn't show that in this talk because of time constraints, but one thing I prove is that distance centrality measure on a tree, the distance center is equivalent to the rumor center. They're actually the same thing on the tree. On these general networks, I actually, I didn't show it here also, I tried distance centrality as an estimator, and that actually does worse than rumor centrality. So I didn't include that here in this talk, but I have shown that result to be true.
She asked about degree centrality.
So degree centrality, I didn't try at all. And I imagine it would be a pretty weak estimator because if you pick one of these guys by chance, then you would never ever pick that as the source because if it hits one of these hubs, it'd always be biased. It'd be biased towards this guy.
So does your theorem that says that if you always choose between the centrality in the regular trees, then it will take the same error with this method?
So in the regular trees, it would be the same error, right? Because they're equivalent nodes in the network. Question?
Do you have any information about what types of errors you make? That, for example, a natural hypothesis would be that if your rumor actually started somewhere on the periphery, that rumor centrality might lead to picking, the first place in the hub that the rumor actually reached.
Right.
Do you
So
have any data about that?
theoretically, I haven't analyzed this estimator on a general graph because it's just a really complex thing that I think at the end of the program, I felt like it was more important to show kind of empirical performance. So I haven't looked at that question yet, but I think it's a great thing explores how this performs on general graphs, how the structure gives you the ability to infer when there's cycles involved. Oh, one more question.
So my understanding is that the AI's graph is almost a tree. It's like
It is very tree-like. That is true.
It's essentially a tree with a handful of cross edges.
It's tree-like, and it's very there's a lot of hubs with very high degree, and then very low degree nodes. So it is very tree-like structure. Okay. So next I look at a power grid network. So in this network, the spreading, you can think of it as being a cascading failure going through your power grid. Again, the same kind of experiment. Rumor centrality with this BFS spreading order. And now you see even I get better improvement in the performance, right? I get 20% or 40% within 2 hops of the source. And I get the correct detection with this correction for this BFS spreading order. And finally, I just tried just for fun my Facebook network. So this isn't too big a network. It's only 130 people. So I can only spread to 50 nodes in this network and just try the 2 estimators. But again, you see with this BFS spreading order correction, I've increased correct detection to a decent percentage. All right, so let me summarize this part of the talk. So I developed this ML estimator for the rumor source in a network, this rumor centrality. And I kind of showed there's this detection threshold for this problem. So for linear graphs with no growth, there's essentially no detection asymptotically. But if you get some growth in your graph, then you can get detection always. And finally, I kind of extended this estimator to a general graph. And this showed empirically it has decent performance and a lot of real topologies. Okay, so that's it for rumor sources. So now let's move on to superstars. Okay, so this part of the talk is going to be in the context of Twitter. So for those who don't know what Twitter is, it's a website where you can share information in the form of tweets, these 140 character messages. So I might tweet at MSR Newland today. And then on Twitter, there's things called retweets. So a retweet is when somebody forwards my tweet. So maybe some people retweet me, right?
Yeah.
And what's nice about a retweet is that a retweet lets you track the flow of information, right? It's a measurable thing. You can measure somebody retweeting me. So what I decided to do was actually look at retweets on Twitter.
Did you on purpose have some of the retweets having typos?
I did?
Did he?
Oh, day.
Jennifer is
Oops.
ran out of cards.
That was the problem with the Twitter servers, I guess.
That's
Twitter.
That's a pretty good indication of how I tweet or IM people. So let's go on.
You get to Twitter problem. Okay, so retweet networks. So here's what I did. So when I was in this summer at MSR Cambridge, I was basically collecting like a lot of retweets, and I decided let me just pick a topic and collect retweets about some specific topic in real time. So for example, during the Wimbledon, in the first round of Federer's match, I would collect any retweet with the word Federer in the text of the retweet, right? And because a retweet is essentially an edge, right? It has a tweeter and a retweeter. You can just stitch them together to make a network, okay? So I did this for Federer, England during one of his matches in the World Cup, the BET Award show this summer, and the World Cup during the World Cup opening ceremony. So I got all these retweet networks. And what I wanted to ask was, what models the growth of these networks? Like, is there a way that describes how they grow? Now, the very common network growth model is this thing called preferential attachment.
Visualization of these nodes in the network, that's you're doing or something?
This is a program called PageEck. So you just give it a network, it gives you different kinds of visualizations.
Okay, so the fact that I see some spiraling over there, but not here, is not something that you arranged?
Nothing I did, just the algorithm that does that in the visualization itself.
Do we know what it means?
So just here, basically, it tries to minimize like an energy of a spring-based system, but you can't say quantitatively what it means now. But you can kind of see some. You can kind of get some foreshadow what's going to happen. You see like some centers, right? Some like.
The Twitter network is not symmetric, though. I mean, in the sense that different people have different numbers of followers.
Exactly. So the underlying network is not symmetric, right. But I thought let me just look at these networks and maybe something interesting happens. So I thought maybe I could use preferential attachment to model how these networks grow. So this model is proposed by Barbasi Albert in '99. And this model, basically a new guy comes to my network, and with a probability proportional to that node's degree, he joins that node. So for example, if this is my network, then the attachment probabilities would be given by these values on this network. If a new guy comes, then you update the distributions of attachment to these numbers, right? And a property of this preferential attachment networks is that the degree distribution follows what's known as a power law. So if I pick a node at random from a preferential attachment network with a probability roughly d to the minus alpha, it has degree d. And this model is really great for modeling things like the World Wide Web and the power grid. So I thought, let me just try this model on Twitter and see if it gives me the same kind of structural properties. So that's what I did. So here's the results of my empirical retweet data in black. This is the degree distribution on a log-log scale. And here's the preferential attachment network of the equivalent size of the Twitter network. So on a log-log scale, if you see a straight line like this, it indicates a power law. So I'm getting a power law, and I'm pretty close to the slope. So I thought, great, I have a model that works. But there's something else here that isn't obvious visually initially, but if you look closely, you see it. And that's every retweet network has one really high degree node. I call them superstars, right? They're way out here. They have really high degree. And these superstars aren't present in preferential attachment. So in preferential attachment, if you have like an n node network, then roughly the max degree is root n. But these guys, looks like I'm scaling degree by n here. They look like they're order n almost. It's beyond 10%, sometimes 50, sometimes higher. So what is giving me a superstar in Twitter? So I need a new network growth model clearly. So I thought, let me kind of back up and think about stuff. And this led me to this idea of syntax versus semantics. All right, so preferential attachment uses degree to grow the network. But degree is like a local or syntactic property. What do I mean by that? It's like, I think people with a lot of friends are important. I don't care who the friends are, right? I just care how many you have. It's like the syntax, the number of friends matters, right? But in a social setting, that is not the case. What matters is the global or semantic properties, right? In other words, I think people with important friends are important, right? It's the whole structure of the graph and how you sit in that structure that matters to me in a social setting. So this idea of importance led me to propose a new kind of network growth model. And I call this model topological network growth, right? And here in the model is very like preferential attachments that I come to the node, a network, and I attach to a guy in the network proportional to his importance function I of v, right? But what should I use for I of v? What's a good importance function? Well, let's think for a second. I want something that kind of incorporates the global topology of the network, right? So what kind of function does that? Well, as I've already shown you, these network centralities really they kind of capture this kind of thing. So let's try that, right? Let's try network centrality as an importance function. But there's many kinds of network centrality out there, right? So which one do I pick? There's degree centrality, which is your node degree. So that's just preferential attachment again, right? There's distance centrality. So this measures how close you are to the other guys in the network. There's page rank. So page rank is a measure that kind of measures how often a random walk on the network hits my node. And there's rumor centrality, which is the likelihood of being a rumor source. So I thought, let me just try these measures, run a simulation of the same size as the Twitter data, and see which one works, right? Very scientific approach. So first I plot here the superstar nodes. So these bar charts show in the green the actual superstar degree in the Twitter network. And then the 4 bars here are the superstars in the centrality networks, right? And what you notice is that immediately only one guy has a superstar, right? It's only the rumor centrality. These other guys don't even come close. So this gives me a sense that maybe.
Are you maintaining the directed nature of this, or are you
So
changing it to an undirected graph?
in this model, I basically take the graph. I basically pretend it's undirected when I grow it, right? So it's an undirected graph I'm looking at. So on the undirected graph, they are actually similar. They're the same. So I realized that later, post facto. On an undirected graph, actually, it's like the stationary distribution of a Markov chain. So they actually become the same. On a directed graph, they are different, though. I agree. And on a weighted graph, they can definitely have different things happening. So this is undirected network, unweighted graph. So okay, so I'm getting a superstar with the rumor centrality.
Page rank has no restarts because with restarts they're not the same, right? Without restarts.
Right, when you add a uniform piece to it, the restart at a uniform site.
So in this case, I didn't consider a restart. I basically considered just take the network.
0 restart, so you can get stuck if you're doing your.
Yeah.
Oh, but it's undirected.
Undirected, so you don't get
you
stuck.
can walk back
And
out.
they're clearly not the same if you look at them.
Well, these are just instances of a random simulation, right? So it's possible that they get different.
It didn't converge or something.
Right, this is only 500 to 3,000 nodes. So
What's the first column?
first column is the data. It's the green is the Twitter data. So I'm trying to match this bar. This is the simulations in the blue. And the superstar rumor centrality is the coming closest. Not exactly, but same order, right? So now let's look at the rest of the graph, see if I get the degree distribution. So here it is, right? This is the 4 networks, the degree distribution for the rumor centrality network in blue, the retweets in black. And you see that I'm getting the superstar pretty close. And also, I'm getting the power law almost like dead on. And this is like across all these topics, right? Soccer, music, tennis, right? It's really just, I kind of stepped back for a second when I saw this. Like, wow, that's really interesting, right? So it seems like this rumor centrality kind of is a good model for Twitter, right?
Now, is that your original rumor centrality?
Exactly.
Or is that approximation?
The original one, right? That formula with the n factorial over the.
Without the extra.
Without the BFS fraction,
heuristic.
just the structural thing.
How can you calculate the precise one on this big graph?
So actually, there's a message passing algorithm that calculates rumor centrality for every node in my network in order n time.
Good.
So you can do it really fast.
Yes.
All right. So I thought now, okay, this was really crazy. Let's look at what rumor centrality does to give me those things. Give me the superstar, give me the power law. So a little bit more theory now, if you don't mind. Oh, question?
Sorry, let me just understand properly the retweets thing. So it's just when you post something and then it's forwarded, and then if that's forwarded again, you're counting the entire network, right?
Right.
So like the 505 is when you post something about Federer.
So when I look at Federer,
that'll be retweeted 505.
Well, it says when I look at the Federer over that time period of his match, that network of retweets had 505 nodes in it, right?
Okay, and the retweets are of a specific message, or?
So here's the thing. So I was looking for any retweet with the word Federer in the text. So it's not one tweet being spread around. It's any kind of tweet about Federer in that time window, right? So that's how.
Being exogenous topics, because these are happening real time, external, which means they're not necessarily related to one another that they're posting. So for example, hashtag things black people say would be an endogenous topic where you would only be responding to it if you've seen it within the graph. Whereas you might be posting on Federer having no idea that anybody else is talking about it.
That's true,
You're
right?
watching it real time.
But these are all retweets though.
Well, but he's not looking at them as directed retweets.
Right. So it's just any retweet out there I put in this graph.
He's effectively looking at them on topic.
So I'm kind of looking at the kind of large scale.
But if they're the retweet,
But if
they're coming
they're-
from within the network. someone within the network. He's not looking at the same retweet as it flows.
Right.
No, but they are.
So one thing I found
Probably more than
related
one
to the
source.
network.
Like if
But they're related to somebody else.
Okay, we should let him, yeah. Okay, sorry.
But just to answer that question, so one thing I didn't mention here is that these networks actually have a lot of connected components. So this 505 here, I'm looking at the biggest connected component. And I saw in all these networks that they have one huge connecting component, and then a lot of small, like 10 nodes, 15 nodes, a lot of edges also, like 2-node graphs. So let me look at this biggest guy and see what's happening there. That seems to be what the action is. Okay, so now let's look a little more theory. So sorry for the people that don't like theory in the audience, but let's get a little bit of it. So what I've shown for this model is that this structure here is a fixed point of the model. As in, if you get to this point in your growth process, it stays in this point. So let me kind of explain what this fixed point is in a little more detail. So first, I have a superstar node in my fixed point. Right? I have one superstar node. His degree is n by 2 plus small o of n. Right? So it's roughly half the nodes connected to the superstar. Okay. Then the guys that neighbor my superstar, which is roughly half the network, they are roots of subtrees. And most of the subtrees have small o of root n nodes. They're not too big. A few of them, a finite amount, have little o of n nodes. So they're like quasi-stars. Okay? And then beyond 2 hops of my superstar, in this yellow region here, there's only small o of root n nodes kind of scattered throughout. So this is a fixed point of my model. So let's say this fixed point gives me the things. Right, so after n nodes are in the network, this is the structure I've seen as a fixed point, empirically and also theoretically. So let's say this gives me the superstar.
What does theoretically mean?
Theoretically means that what I've shown precisely is that if the model reaches this point at any point in the growth process, this kind of asymptotic structure, it stays in this asymptotic structure. Like another superstar is not going to emerge out of here, right? It's going to stay in this kind of structure.
So it's stationary.
What I haven't shown is that it actually gets to this fixed point every time. That result I haven't established yet because it's kind of hard to show that because the growth measure is so like global and not local that it's not like preferential attachment, it's a bit easier to analyze comparatively. So I haven't shown that part yet. That's a nice theory question to answer though. It's like how does this reach the fixed point?
And the graph is always, you're modeling it as a tree or as a
tree. So it's assuming it's a tree-like structure. Okay, so let's look at how we get superstars first. So for superstars, maybe an easier way to begin looking at this is not that whole messy fixed point structure. Let's consider a simple star network here. So in the star network, right, if I have n guys around that superstar guy in blue, then his rumor centrality, the superstar, is n factorial. There's n guys here, you can order them n factorial ways. One of these guys on the boundary here, the leaves, they have n minus 1 factorial of rumor centrality. So if I calculate the attachment probability for the superstar, it's by this expression, n factorial, which is his rumor centrality, over n factorial plus n minus 1 factorial times the n guys around him. But this is just a half. So in this simple network, with a probability a half, I join the superstar, right? And in fact, in the whole fixed point structure, if you analyze it, it's actually a half times a small correction, 1 minus O1 over n. Okay? And to see this more visually, here's a simulation of the first 4 nodes in the rumor centrality network. Their degree is a function of time. And you see one guy is like growing linearly with slope a half, which is that probability. That's my superstar. These other guys here are growing a lot slower. In fact, they're growing sublinearly, you can see. So that's how we get a superstar out of this model. So how about the power law? Right? So why don't we look at the attachment probabilities of 2 neighbors of my superstar, nodes u and v that neighbor the superstar, right? So this ratio, this is the ratio of the rumor centralities, right? Now I can show that this ratio is actually given by the ratio of their subtree sizes times the inverse ratio of n minus their subtree sizes, just using the properties of rumor centrality to get from this to this.
There's something that's confusing me a little bit. In a lot of these, you're treating the expectation. You're not showing concentration really. You're treating it as if you can look at the expectation.
Right. So all this analysis thus far has been kind of like in the mean, right?
Right. Which is not. I mean, what you would need to do to establish that this is correct is you would have to show that there's sufficient concentration that this is.
Like I said, this is like kind of preliminary theoretical work in this new kind of graph.
It's theoretical. It's not quite yet.
It's not there yet.
It's not quite yet theorems, but it's.
So maybe it's like
but it gives you a good indication of what the theorems might be.
So let's call it a physics proof, maybe.
Yes.
Physics proof. If that's okay to everybody.
And I love physics proof, so that's not bad, but yeah.
So this is like preferential attachment for them or something like
Well, good intuition, right? So,
Yeah.
as you said, this is the ratio. This is this
Yeah.
ratio. So, as I said, in the fixed point, n is much bigger than any subtree. So I ignore these guys. So it's roughly the ratio of the subtrees. Because it's only like order small o of root n guys scattered throughout, your subtree size for these neighbors, the superstar, is roughly equivalent to your degree. So as you said, it's like preferential attachment. In fact, what happens is the guys neighboring a superstar, they're seeing preferential attachment amongst themselves, and they're roughly half the network. So that's how we get the power law kind of pops up out of the degree distribution. Okay, so now let me end this part of the talk with kind of my thoughts why I think rumor centrality is working so well to find these, or describe these networks. So first consider the World Wide Web, right? So in this network originally, the main feature people measured was this power law in the degree distribution. And from that, they got this preferential attachment model where like the number of links pointing to you was like the importance function, right? And if this is the importance function, like the natural centrality measure are things like page rank or degree centrality, which are very related to each other. So why this is practical is that you can use things like PageRank to do web search, right? So now let's think about Twitter, right? So on Twitter, what are the features I measure? I measure the power law and the superstar, right? So what is the importance function that kind of modeled this? Well, my hypothesis is that it was the likelihood of you being the source. It's like people come to Twitter and they kind of retweet the guy that's most likely to have been the source. Not exactly, but maybe abstractly, that's what they're doing implicitly. If that's the case, maybe that's why rumor centrality is working so well to kind of describe these different networks and different topics. And now what's the practical use? Well, first thing is, right, search. You could use this measure to like do kind of search on Twitter for different topics. But remember on Twitter, these aren't websites. They're people, right? So maybe I can do things like influence measure. I can measure someone's influence quantitatively with this rumor centrality perhaps. Why is that really neat? Well, you think about taking this quantitative influence measure and doing kind of target advertising. Like if I'm a company that give you a coupon and the discount on the coupon is a function of your rumor centrality or some kind of creative things like that, right? There's so many things you can try to do with this now that we have this.
Only give it to good.
Yeah. All right. So that's it for superstars. So now I'm going to wrap up this talk, with communities. Okay, so real fast. So communities and networks, right? So what properties should a community have, right? So the old view has been that a community should be a bunch of nodes in a graph densely connected to each other without too many inter-community edges. So there's not too many edges out of the community between communities. And this view of communities...
If it's okay with people, since we have interrupted so much, I'd like to give them an extra 5 minutes so let them have
I think I
10
can finish
minutes.
at 10. I think 10 I can do it.
Yeah, okay.
Sorry.
So you have till 5 after, which is 10 minutes.
Okay. All right, so these properties of communities lead to this notion of a graph cut. Right? So what's a graph cut? So if I have a network here where like communities are clearly visible, these clicks, I can cut the graph there to kind of cut off a community. And what you do is you want to find a community by minimizing the size of a weighted graph cut. So you kind of take this cut and you weight it by the size of this community in it. And the problem is kind of minimizing these weighted graph cuts is an NP hard problem. So what the people do is they approximate it with this technique called spectral clustering. And this tries to approximate those minimum weighted cuts. It's called spectral because it's using the eigenvalue of the graph Laplacian matrix to do the clustering. It's a great algorithm, but it has one weakness. And that is I have to tell it how many communities I want, how many cuts to make. What I'd like is an algorithm that kind of takes the network and figures out and so on how many cuts to make. So this led me to kind of re-examine what a community is. So now what properties should a community have? And here's my view. I still think people in the community should know each other. Call me old-fashioned. But I don't really care about these inter-community edges. I don't care how many friends you have outside the community, as long as there's one internal property we maintain. And that's a loyal follower. So it's a node in a community with no neighbors outside the community. So for example, in this network here, the loyal followers would be these red guys. Because they're not really bridging the communities, they're internal with the community. And I got this idea by looking at my Facebook network and figuring out what distinguishes my different social circles. It's these people that kind of don't mix outside the circle that gives that group its identity. It's like the detectable signal of that community. So if I have followers in a network, I must have leaders also, right? But how do I distinguish a leader from a follower? So locally, a leader is more important than a follower because he's like the bridge to community, between communities. So I thought maybe I could use network centrality to kind of find leaders and followers. Right? The problem was I couldn't use it by itself. I'd use it in a differential sense. And here's what I mean by that. So network centrality on its own cannot find you leaders and followers because its value depends upon the size of the community. For example, in this network here, right, I have 3 communities, different colors, with the loyal followers indicated. This is the degree of the nodes in the network. And you see like the degree kind of relates to the size of your community. So just the value of degrees that could tell me who's a leader, who's a follower. But I say within a community, the leaders locally more important. So maybe a differential measurement will give me the leaders and followers. For example, I take that same plot, I replot it, I group the nodes by community and color them. The local minima in each color group is the loyal follower. So I do local comparisons, maybe I can figure out a leader and a follower. So this observation led me to this leader-follower algorithm to find communities. So it has 2 stages. First, I'll find leaders and the followers. And then I'll just assign nodes to the leaders to form communities. So let me walk you through this to see how it works. So let's assume this is my example network where there's 2 communities clearly visible, these 2 cliques here. So first, I'm going to use degree centrality as the importance of the node. And I'll say that if a node has a higher importance than at least one of his neighbors, right, you beat one guy at least, you're a leader. Otherwise, you're a follower. So with that step, these 4 guys are going to be leaders. They have a higher degree than at least one neighbor. Okay? So I found leaders and followers. Now I'm going to assign nodes to the leaders. So what I do is I rank the leaders in order of decreasing importance, and then it's like a draft. So they all pick their followers, the neighbor them. So V1 would pick all those guys. V2 can't get anybody now. V3 gets that guy, and V4 gets nobody. So now I got leaders, V2 and V4, that have no followers. So they're not leaders anymore. So what they do is they just join the majority of their neighboring followers, right? They follow the followers. So they join 1, he joins 3. And now in a general network, I might have some guys that didn't neighbor any followers at all. They only neighbor leaders. So they just join the majority of their neighbors with ties broken arbitrarily. Right? And after that, you'll have your communities like that. Now this algorithm, I can actually give you some theoretical guarantees for it. So I established the following result. If a network has disjoint communities that satisfy the following 2 properties. Every community is a clique, and every community has at least 1 loyal follower. And then the leader-follower algorithm will detect these communities exactly.
It's kind of unlikely, though, when you look at actual networks, that
Great,
your
right?
communities are cliques, right?
Not matter disjoint.
What?
They're not disjoint.
Well, these, right, but I'm saying, I mean, sometimes people define things so
Great
that
point,
there are
Jennifer.
disjoint
And
communities, sometimes so that they're not, but it's really a lot to ask that it be a clique.
So right now we're trying to...
I thought the point is that every person belongs to several, well, I guess the sum of the people are followers and only belong to one community, but most people belong to several communities.
Right, so we'll get to that question in a little bit. But right now I can establish this kind of theoretical result for this algorithm. That in this class of networks, it works, right?
So let me understand. So what you have is you have disjoint cliques, and then you join them by edges as long as it doesn't create more cliques.
As long, you can create more cliques, but as long as the original cliques maintain at least 1 loyal follower. Then no matter how you connect them up, in any arbitrary way, it always finds those initial communities.
Oh, so you can start with any cliques.
Any cliques.
And now I can add edges as long as I can create new cliques, but I
Exactly.
just have to make sure that the original cliques have 1 loyal follower left.
Then no matter what you do, I'll always find your communities.
But then there is a very simple algorithm. No, I mean, because the neighborhood of at least every clique is the exact neighborhood of at least 1 vertex. So if you go over the neighborhoods of every vertex and enumerate them and see if there are cliques, you'll output your...
Well, you could have a situation where you have like a clique formed by the extra edges.
Ah, but it's not, it wasn't a clique in the original.
Right.
I see. Okay, we should probably, since,
Yeah.
you know,
Okay, so
sorry, I started.
what I show is that I kind of compared this algorithm to spectral clustering just to see how they perform. What I found is that when there's a lot of dense intercommunity edges, spectral clustering, because it's talking about minimizing cuts, it actually fails. So like these pictures here's like a sparse network, dense network. With the dense guy, you see like spectral clustering actually merges the whole graph together into one big community. Right? So it's actually missing this finer community structure, spectral clustering. Whereas my algorithm maintains all these communities. It finds them every time, no matter how you connect them. All right, so now you talked about real data, so let's talk about a real network. So I tried my Facebook network, right? So I said, let me take my network, apply the algorithm to it, leader follower, and see what I get. So I got a bunch of communities out of it. And because I knew these people, I would just kind of go through the people and just kind of label what I think was the unifying theme. So like my master's research group, my PhD research group, from friends from Berkeley Music College, high school friends, etc. To compare this, because it's kind of an arbitrary labeling, I took the same number of communities I found here as input to spectral clustering, applied spectral clustering, and you see what happens is that for the sparse communities, it didn't really mess up that much. But for these dense part of my network, it kind of merges the whole thing into one thing. So again, it's missing the finer structure. And now one more really cool thing I tried was a human brain network. So in this network, every node is like a point in the brain, and there's an edge between two nodes, and there's like a sufficient correlation between them in a functional MRI scan. So I got this data from some folks at MGH, and I just tried it, right? So leader-follower algorithm found a lot of communities, but some of the bigger ones it found actually corresponded to real brain functional regions, occipital lobe, frontal lobe, temporal lobe. Spectral clustering with the same number of communities totally misses the temporal lobe, right? So again, we see it's missing its finer community structure that.
Not an expert on spectral clustering, but is there like just one algorithm that's called spectral clustering, or maybe you can tweak it when you're trying to find like?
It's actually different kind of algorithms, because you use different kinds of cuts basically, but they're all kind of weighted cuts. So the general technique is you take whatever cut you want, you use the graph Laplacian in a certain manner to get the clusters.
Should we let him finish his thought? Yeah.
Yeah, I mean, we can, Chris and I can talk to people afterwards. We have done variants of spectral clustering for communities. We tried very hard with John Hopcroft, Shanghua Teng, a lot of people. It's not obvious. Okay, so yes, people do variants. And they probably miss the temporal lobe too, so go on.
Okay. All right, so let's wrap up the algorithm strengths. So you don't got to tell it how many communities you want. It learns that from the structure naturally. It can find this finer structure that spectral clustering couldn't find. It has theoretical guarantees for a certain class of networks. And most importantly, it's a fast algorithm, right? It runs in order E time for E edges. So you can imagine taking all of Twitter or all of Facebook and just trying to cluster the whole thing, which would be kind of neat to try. All right, so let me just wrap up here. So I used network centrality to extract knowledge from networks. So for rumor source detection, I created a new centrality measure, this rumor centrality. For superstar prediction, I created a new network growth model using centralities. I kind of modeled Twitter nicely. And then finally, for community detection, I use these local differences in the network centrality to find communities with leader follower. So I guess this is my last slide. I'll just talk about future stuff I want to do. So the whole theme of this talk has been structure in networks and knowledge in networks. And like my ultimate goal is to kind of like develop kind of a large-scale knowledge extraction system. So like a system where you give it things like Facebook or Twitter, any kind of general network data, and they give you a lot of outputs. So the first kind of output I'd like to have is like structural knowledge. Things we talked about here, communities, rumor sources, superstars. But the thing I didn't talk about yet, which I want to kind of dive into in the future, is temporal knowledge. Things like how fast does something grow, how fast it spread, etc. And then I think connecting structural and temporal knowledge is like a really neat theoretical question to analyze. But also practically, with that kind of connection established, you could do prediction. Like you could predict who's going to be a superstar, which is the original goal of this talk, how long it takes to become a superstar, or more generally, just how things spread in a network if you connect structure and temporal. And I feel like with the vast amount of data available already in Twitter, and also the pattern I've seen emerging, this kind of prediction should be something that could be done. And I think it's really exciting to give it a shot. Question?
Taking one more step. How can I get to be a superstar?
Well, that's natural extension.
You just need to tell us how you did it.
So, but that'll be future work in the future, becoming a superstar. So with that, I'll just end here and take any questions you have. Yeah, sorry for going over.
So I have a question. I mean, I could propose another model to accurately match Twitter data, which is with probability a half, say.
Exactly.
I connect to this special node. Otherwise, I follow a preferential adaptation model.
Pretty much what it is, right? This model, when you look at it. The reason.
And this could also maybe match better data that are kind of biased. Say, when you have more context, like I prefer Federer to Nadal, or I prefer Nadal to Federer. So you have two nodes, and then.
So the reason I didn't want to do that kind of model initially, because what I wanted was like a structural model. I wanted a model that had no parameters in it, no free parameters. I wanted a model that takes the structure and then models the growth with just that structure. So it's more of a physics kind of approach, like the underlying thing. So that was my goal in proposing rumor centrality as like the measure, right? But I agree, in the end, it looks like just a half I pick this guy, and then the half I do a preferential attachment. But it's nice that you can connect it to the actual topological property, which is why I kind of like this model.
I really enjoyed this because it's really interesting to think about. But it seems that it's fundamental that you're using a transmission model of communication.
Right.
That's fundamentally what you're doing. I'm wondering, did you know that, and have you thought about the critiques of that model in communication theory, and how would you account for theories that really talk about a kind of interactional approach to communication and meaning?
Right. So
I mean, maybe that's beyond what you need to do into this, but that's a fundamental
That was the
assumption.
first question I
It
was
was?
asking
Oh,
him,
okay.
actually. But yeah, other people have done that a little bit, yeah.
I mean, the goal is that whatever I do, I want to kind of approach it in a scientific manner. So if you propose that kind of model for communication, you want to kind of check in the data, is that model happening? And then kind of try to understand, hypothesize what the model implies for algorithms, for things like that. So I agree, if that's the model you want, then you should kind of approach it in that manner.